On the 26th of June, 1943, over the French coast at 20,000 feet, a Focke-Wulf 190 closed in behind a Republic P-47 Thunderbolt and opened fire. The pilot of the Thunderbolt was Second Lieutenant Robert S. Johnson of the 56 Fighter Group. By the time the attack was finished, his aircraft had absorbed more than 200 hits from cannon and machine gun fire. The hydraulic system was gone. The canopy had taken a round that jammed it shut. The flaps were destroyed. The aircraft was, by any rational assessment of combat damage, no longer capable of sustained flight. It was still flying. Johnson held the controls against a column, fighting him in directions it should not have been moving, nursed the throttle, and made for England. The German pilot, who had climbed back into position and found his ammunition exhausted, pulled alongside and looked at what his guns had produced. He held station for a long moment, examining the holes and the trailing fuel and the surfaces hanging at wrong angles. Then he waggled his wings and turned for home. The wreckage beside him was still airborne. Johnson landed at Manston with no brakes, rolled through the boundary fence, and sat in the cockpit while the ground crew came out to find him. They walked around the aircraft and counted the damage. The count produced a number the men present could not argue with. What they needed was an explanation for how the number was possible. If this story is pulling you in, take a second to hit the like button and subscribe, and drop a comment telling me where in the world you're watching from. It means a great deal to know who's listening. The question the Manston crew chiefs were working around, without having a framework to frame it precisely, was the same question German fighter pilots across occupied France had been noting in their after-action reports for months. What kept these aircraft in the air? The Thunderbolt's reputation for absorbing damage that grounded other fighters had been building in the operational records on both sides since the 56 flew its first missions over France in April of that year. P-47s came home with engine cylinders shot away, with tail surfaces so damaged that pilots felt the controls pulling sideways on final approach, with hydraulic systems running on residual pressure since somewhere over the channel, and fuel trailing from wing punctures that should, by any calculation available to the men examining the fuel gauges, have depleted the tanks well before the aircraft reached the English coast. The answer was not in the cockpit. Courage and training could not account for what the maintenance logs were recording and what German gunnery analysis was noting with increasing precision across the spring of that year. Aircraft correctly struck in the engine compartment that did not slow down and did not show the symptoms liquid-cooled fighters showed after taking equivalent fire. The answer was in the engine. And to understand the engine requires understanding the problem Kartveli was working on when he began the design, and what the solution he chose produced as a consequence of decisions made for reasons that had nothing to do with combat damage at all. In the late 1930s, the Army Air Corps understood one essential fact about the air war approaching it. Altitude would decide the engagements. Whoever could fight above 25,000 feet would control the airspace. And controlling that altitude required an engine that could breathe where the air held less than a third of the oxygen available at sea level. Normally aspirated piston engines lost power progressively as they climbed, the fuel mixture going wrong, the combustion losing efficiency, the horsepower falling to fractions of what the same engine produced on the ground. A fighter built around such an engine was effective at medium altitude and a marginal proposition above 20,000 feet. The next war's air battles were going to be decided above 20,000 feet. Everyone in a senior technical position understood this, and the understanding had not yet produced a solution. The Battle of Britain in the summer and autumn of 1940 had made this arithmetic visible to anyone paying attention. The engagements over southern England were decided in the vertical. Aircraft that could reach altitude faster and hold it longer controlled the terms of the engagement. The Luftwaffe's bombers, heavy and slow and constrained by their service ceilings, were consistently vulnerable to fighters that had the height advantage and the energy to press it. American air planners watching those results understood that the next air war would be settled in the same dimension. The aircraft that owned the high altitude would own the airspace below it. The Air Corps needed an engine that could work at that altitude, and it needed one now. The solution in principle was supercharging. Compress incoming air and feed it to the engine under pressure, so that the engine behaves as though it is still operating in the denser air of lower altitude. The British had built gear-driven supercharger stages into the Rolls-Royce Merlin that powered the Spitfire, and the arrangement worked well through the altitude bands the Battle of Britain required. General Electric in the United States had developed a different approach. Their turbo-supercharger was driven not by a mechanical connection to the crankshaft, but by exhaust gases the engine expelled, which meant it could maintain higher power output at altitudes where the gear-driven designs of the period lost efficiency. It was the better solution for sustained high-altitude operation. The difficulty was not its performance. The difficulty was the volume it occupied. The complete turbo-supercharger installation was larger than anything the aircraft design practice of 1938 had a clean answer for. The turbine unit itself was the size of a substantial piece of furniture. The ducting required to carry exhaust gases from the engine aft to the turbine and compressed air from the turbine forward to the engine ran to dozens of feet of metal pipe that could not be shortened without degrading the system's function. The intercoolers that prevented the compressed air from arriving at the engine cylinders too hot to be useful added bulk that could not be eliminated without eliminating the performance advantage the system was designed to provide. When the complete installation was laid out for integration into an airframe, it presented a problem that no existing fighter design of the period could absorb without losing capabilities the Air Corps had specified as non-negotiable. Alexander Kartveli was chief designer at Republic Aviation on Long Island when this problem landed on his desk. He had been born in Tbilisi in 1896, trained in aeronautical engineering in Paris after the First War, and had come to the United States in the 1920s with a thorough background in European aircraft design practice and the patience of an engineer who understood the difference between a constraint that was genuinely fixed and one that looked fixed because the framing of the problem had not yet been questioned. He had designed the P-35, a monoplane that was among the faster American fighters of the mid-30s and obsolete before the decade ended. He had also produced aircraft the Air Corps had declined to put into full production, proposals technically sound enough to earn further development, but whose timing had not aligned with the service's procurement cycles in the years of lean budgets and limited interest. By 1940, he had a working engineer's understanding of what American military aviation needed and what the procurement system had not yet decided to buy. He was working on the aircraft that would succeed the P-35, and every approach to the supercharger integration problem returned to the same wall. The installation was simply too large for any airframe he could design to the Air Corps' other requirements without producing an aircraft that failed on one of those requirements or another. Kartveli changed the framing. He stopped asking how to fit the supercharger installation into a conventional airframe and began asking what kind of airframe was large enough to house the installation as its structural core, with the aircraft's other requirements worked around what space remained. The fuselage of the P-47 was dimensioned from the beginning of the design process to contain the complete turbo-supercharger system. Exhaust ducting ran aft along the lower fuselage on both sides of the centerline to the turbine mounted behind the cockpit. Compressed air returned forward through intercooler ducts along the belly. The intake and return paths were not added to the fuselage structure, but built into it at the design stage, integrated rather than mounted. The cockpit sat high above a fuselage that was deep because the machinery below the pilot seat required that depth, and wide because the ducting required that width. Every dimension that made the aircraft look wrong by the standards of the day followed from this decision. The Spitfire weighed approximately 6,000 pounds in combat configuration. The P-47, before its 850 caliber machine guns were loaded and before its fuel tanks were filled, already approached 12,000 pounds. Combat ready, the figure exceeded 14,000. The pilots who first encountered it at Duxford in December of 1942 came from Spitfires, and their accounts from that period carry a register that ranges from perplexity to open alarm. Several pilots who flew early familiarization flights described the experience in terms the Army Air Corps' Public Affairs Office would not have found useful. The aircraft's weight could be felt on every control input. It climbed as though it was aware of how much it weighed. Pilots transitioning from Spitfires found the landing particularly demanding, the approach speed higher than anything they had flown in combat service, and the runway ahead invisible behind the cowling until the side slip displaced it into view. Colonel Chesley Peterson, an American who had been flying combat missions in RAF aircraft since before the United States entered the war, described sitting in the Thunderbolt cockpit after years in Spitfires as the difference between a tailor jacket and a hotel lobby. The engine cowling ahead of the pilot seat was a cylinder of such diameter that it completely blocked the runway during the landing rollout, requiring a deliberate side slip to see past it on approach. The aircraft climbed at rates experienced fighter pilots found difficult to account for in favorable terms. In the published accounts of the transition period, the word that appears most often is reluctant. At medium altitude, the 190 could outturn the Thunderbolt in a sustained engagement. The Messerschmitt 109G series could match or exceed its rate of climb below 20,000 feet. A turning fight at 15,000 feet, which was where much of the early combat over France took place, favored the 190 substantially enough that a pilot who allowed himself to be drawn into one was in genuine difficulty. German units over France in the spring of 1943 noted these characteristics and recorded them with the precision of professionals who found the information operationally useful. After-action reports from JG2 through the early months of that year described the Thunderbolt as a large target with handling characteristics at medium altitude that did not require the aggressive countermaneuvering that other American aircraft demanded. One report noted the aircraft's physical size as providing the attacking pilot a wider aim point at the gunnery ranges where most aerial engagements were resolved. The reports were accurate and professionally grounded. They were also drawn entirely from the altitude band where the Thunderbolt's design compromises were most visible, and they said nothing about what the aircraft was above 25,000 feet because the engagements that generated those reports had not been fought at 25,000 feet. Above that altitude, where the turbo-supercharger was maintaining full power output and the Daimler-Benz engines of the 109G series were losing performance to the thinning air, the Thunderbolt's behavior changed in ways the medium-altitude records had not predicted. The aircraft's weight, expressed in a high-altitude dive as momentum that lighter machines could not match, produced speeds in the descent that the 190's aerodynamics did not handle comfortably as compressibility effects began influencing control response. A P-47 pilot with altitude and initiative could push into a dive the German pilot could not safely follow to its bottom, reposition at the base of the dive with an energy state the German aircraft could not match in a zoom climb, and return to the engagement from above on terms that the 190's superior low-speed turning could not reverse. Hub Zemke, commanding the 56 Fighter Group through the summer and autumn of 1943, built the group's tactical identity around these specific parameters. His pilots flew high and held altitude. They accepted the handling disadvantages at medium altitude without attempting to fight on those terms, and they looked for engagements where the aircraft's momentum and the ability to trade altitude for speed were assets the enemy could not counter. The group's results through this period were the best among P-47 units in the 8th Air Force. They flew escort for the bombers and returned with a pattern of outcomes that reflected the specific choices Zemke had made. Engagements initiated from above, breaks from fights that were going wrong executed before the energy deficit became unrecoverable, and a consistent willingness to disengage from an unfavorable engagement in order to set up another on better terms. The tactical approach looked to pilots conditioned to the aggressive close-range fighting of the Spitfire tradition, almost like caution. What it was, measured in the group's results across the operational period, was discipline. Zemke's later accounts described the process as learning to listen to what the aircraft was telling you about where its strengths were, then having the discipline not to fly it anywhere else. He also described, without connecting it to its engineering source, the particular quality the aircraft's behavior in combat gave to the pilots who flew it. A confidence in the machine that changed what risks they were willing to accept under fire and how long they were willing to hold difficult positions before breaking off. That confidence had a specific origin in the engine. And the engine requires understanding in a particular context. What happens to different engine types when cannon shells arrive in the engine compartment, and why the same caliber round landing in the same area of the aircraft produced, in the Thunderbolt, a different result for what it produced in every other fighter operating over Europe. If this is the kind of history you want more of, subscribe and turn on notifications. There's far more in the record still to cover. Your support is what keeps these stories coming. The Pratt & Whitney R2800 double Wasp was an 18-cylinder air-cooled radial engine arranged in 2 rows of 9 cylinders around a central crankcase. In the versions that first went to combat, it produced approximately 2,000 horsepower. Subsequent modifications brought that figure to 2,500 and eventually to 2,800 in the highest-rated variants. It started reliably in any weather the 8th Air Force encountered over England and the continent. It did not develop the oil leaks that grounded aircraft and accumulated in German maintenance logs through the Russian winters as a separate and steady category of operational loss. Gunter Rahl, among the 3 highest-scoring fighter aces in aviation history, flew captured Allied aircraft through a German evaluation program and remarked years later that the most striking difference between those aircraft and the machines he had flown for the Luftwaffe was not performance in the air. It was the quality of construction. The R-2800, in the assessment of every pilot and ground crew member who worked with it, simply did not break the way German engines broke. These were the facts the specifications recorded. What no specification document captured was what the engine did when cannon shells arrived from the rear quarter in combat. The liquid-cooled engines in the other fighters of European service, the Rolls-Royce Merlin and the Spitfire and the Mustang, the Allison and the P-38, the Daimler-Benz DB605 and the Messerschmitt 109, circulated glycol coolant through passages distributed throughout the engine block. A single rifle-caliber round that found one of those passages was sufficient to begin a process with a predictable conclusion. The glycol ran out. The temperature rose. Within minutes, sometimes less, the engine seized. A pilot who felt a hit forward of the cockpit that did not immediately affect the aircraft's handling might be losing coolant through a hole he could not see, the consequence delayed by minutes, but not avoided. Pilots who flew liquid-cooled fighters over occupied territory carried this as a permanent background calculation. A penetrating hit to the engine compartment was not always immediately fatal, but it was, over a span of minutes that could be estimated fairly precisely, almost certainly fatal. The R-2800 had no coolant circuit to puncture. Its cylinders were cooled by air flowing past finned aluminum barrels projecting outward from the crankcase in a ring. If a round struck one cylinder and destroyed it, the engine lost one cylinder out of 18 and continued running on 17. If 2 cylinders were hit, 16 remained. Ground crews examining returned Thunderbolts through the autumn of 1943 found cylinders with portions of the cylinder wall blown entirely away, the aluminum fins shredded to bare stubs, the piston exposed to open air through the gap where the wall had been, the engine having continued to produce usable power through the remainder of the flight. The crankcase, which tied the cylinders together and carried the mechanical output of the entire assembly, sat inside a ring of cylinders that incoming fire had to pass through before it could reach anything that stopped the engine as a system. A round penetrating an outer cylinder encountered the cylinder wall, the combustion space, the far cylinder wall, and whatever access remained to the crankcase beyond. Each layer absorbed and redirected a portion of the energy, carrying the round forward. The geometry of the radial arrangement produced a further consequence that no specification described, and that operational experience had to discover through accumulation. Rounds approaching from the rear quarter, the angle from which pursuing fighters most commonly fired, struck the cooling fins of the rear cylinder row before reaching anything else. Those fins, thin aluminum projections spaced around the circumference of each cylinder, absorbed and deflected small-caliber fire that would otherwise have penetrated further into the engine. Fragments that passed the fins encountered the cylinder walls of the rear row. Fragments that made it through the rear row encountered the air gap separating the 2 rows and the forward row's cylinders beyond. The layered structure filtered incoming fire through successive surfaces in a way that a liquid-cooled engine block, presenting a largely continuous metal face to the same angle of approach, did not. The engine was, in effect, providing its own armor. The armor was distributed across a structure wide enough that rounds aimed at the center of the cowling were often stopped by the geometry of the radial arrangement before they reached the crankcase. German gunnery analysis arrived at this understanding through the accumulation of cases where accurately placed fire had failed to produce the expected result. Reports from JG2 during the summer of 1943 note specifically that P-47 struck in the engine compartment were not showing the coolant loss indicators observable on liquid-cooled aircraft after equivalent hits. We're not losing power in the minutes following the strike, and we're not breaking off combat or going down in the time frame that engine area hits on other aircraft reliably produced. Units began shifting aim to the wing root fuel tanks into the cockpit. An incendiary round reaching the fuel in the wing root could produce a fire the airframe structure could not contain. A round reaching the pilot ended the flight regardless of the engine's condition. The targeting shift was a professional acknowledgement that the conventional approach was not working against this aircraft, and that reaching its actual vulnerabilities required a more difficult gunnery problem than the doctrine had been built to solve. Johnson's return from France remained the most thoroughly documented case of what this combination of factors produced in practice. He brought the aircraft back with hydraulics gone, canopy jammed, tail surfaces so compromised that holding the aircraft on heading required continuous physical effort against a column that was resisting in the wrong direction. The fuel was low. The engine was running. He did not know, during the flight, the full extent of what the ground crew would count afterward. What he knew was that the aircraft was answering his inputs. With effort. With imprecision. But answering. He made the decisions available to a pilot whose aircraft is flying and brought it back to an English runway it had no formal reason to reach. The maintenance records of the 56 Fighter Group through this period read, in aggregate, as documentation of an engineering characteristic the aircraft designers had not specifically targeted when they made the decisions that produced it. Aircraft returned with damage that required days of work and flew again. Aircraft that in a liquid-cooled fighter unit would have been struck from the operational inventory were instead repaired by the ground crews and returned to the flight line. The turnaround cycle stayed lower than comparable figures for other units in part because the category of damage most effective at putting liquid-cooled aircraft permanently out of service was producing a different result in the Thunderbolt. The engine that absorbed the hit kept running. The aircraft that kept flying got home. The pilot who got home flew the next mission. Francis Gabreski flew 193 combat missions in the P-47 before an error of judgment on a low-level strafing pass in July of 1944 sent his propeller into a German runway and put him into a prisoner-of-war camp for the remainder of the conflict. He had not, across those 193 missions, been brought down by the aircraft and pilots he encountered over occupied Europe. He finished his European tour with 28 aerial victories, the highest total any American pilot accumulated in the theater. In post-war accounts, Gabreski returned consistently to the same quality when describing the aircraft. It kept flying when it had reasons not to, it responded when asked, and it gave the pilot a specific category of confidence in combat that he had not found in other aircraft. He also described what that confidence did, over the long arc of a full combat tour, to the way a pilot managed the cumulative weight of sustained operations. The Thunderbolt did not make the arithmetic of repeated missions into dangerous airspace more comfortable. What it did was make the aircraft side of the calculation more solid, more predictable, more present as something a pilot could depend upon when the other variables were not in his favor. For a man flying his 150th mission, that quality had a value no performance specification was built to measure. He was describing, without the engineering vocabulary to name it precisely, the consequence of Kartveli's decision made before any of them sat in a cockpit. Zemke was lost in October of 1944, caught in a severe weather system over Germany that the airframe could not hold against. He spent the end of the war as a prisoner. The 56 Fighter Group, shaped by the tactical doctrine he had developed through 1943, finished the war as the highest-scoring fighter group in the 8th Air Force. Its loss rate through the most contested phase of the air war over France ran lower than the arithmetic of those engagements would have suggested. The Thunderbolt was replaced in the long-range escort role by the Mustang when the Mustang's range, extended by drop tanks and shaped by the Merlin's two-stage supercharger at altitude, made it the correct instrument for the missions reaching into Germany in the spring of 1944. The Thunderbolt moved into the ground attack and close support roles, where its structural depth made it, if anything, better suited than it had been in the air-to-air engagements over France, and where the R-2800's indifference to the kind of damage that anti-aircraft fire and ground-based small arms produced made it the aircraft that fighter-bomber pilots specifically requested when they understood what they were requesting. Anti-aircraft fire reaching the engine compartment from below arrived at angles the radial arrangement's layer geometry handled in the same way it handled fire from the rear, through successive surfaces that absorbed and redirected what they could before what remained reached the crankcase. Aircraft that would have been grounded by a rifle-caliber hit to the coolant system of a liquid-cooled engine flew through ground fire that left the exhaust stacks trailing visible smoke and the engine still delivering power at the end of the strafing run. Kartveli continued working at Republic Aviation after the war. He designed the F-84 Thunderjet, the first American straight-wing jet fighter to reach production service, and the swept-wing Thunderstreak that followed it. He worked on supersonic aerodynamics and high-speed flight problems that bore no structural relation to the turbo-supercharger integration question he had resolved in the late 1930s. He died in New York in September of 1974. His name does not appear in most accounts of the air war that readers encounter. The aircraft he designed appears in those accounts as background, as the instrument that preceded the Mustang, the one that was heavier and slower at medium altitude. 15,000 P-47 Thunderbolts were built before production ended. Fewer than 100 survive today in collections, each one the material record of a design decision made on Long Island before the men who flew them had put on a uniform. Johnson published a memoir after the war. He called it Thunderbolt. In it, he returned to June of 1943, to the German pilot who pulled alongside him over France, and looked at what 200 cannon and machine gun rounds had done to the aircraft beside him. Johnson wrote that he never found out who the pilot was. The man had looked across the gap between the cockpits at the holes and the trailing fuel and the surfaces hanging at wrong angles, had run through whatever calculation the view presented, and turned for home because the calculation had not come out the way it was supposed to. What the arithmetic had not told him was why. The explanation was in 18 cylinders arranged in 2 rings around a crankcase, no coolant circuit to lose, a structural geometry that presented incoming fire with successive layers of material to defeat before reaching the components that mattered, and a fuselage built wide and deep because the machinery inside required both dimensions. The explanation was in a decision made by an engineer on Long Island before the war, working through a problem that had resisted every conventional approach until he changed the approach itself. Kartveli had needed to fit a turbocharger into an airplane. He had built the airplane around the turbocharger. The airplane that resulted was heavier than everything else in those skies and slower at medium altitude and harder to bring down than anything the doctrine on either side had been constructed to account for. The German pilot looked at what he had done with everything he had and turned away. The arithmetic that explained why he had was written into the design. Thank you for staying with us until the end. If what you heard here stayed with you, the other films on your screen carry the story forward. Subscribe if you haven't, and I'll see you in the next one.